hear me? Perfect. So the punchline that we did, that I tried to deliver at the conclusion of my last presentation, was that if you have objects that can self-assemble in a two-dimensional fashion, making like bilayer membranes, then these membranes are macroscopic in the sense there's nothing in the assembly process that cuts off their size. And so they can be very large objects that are stable and don't fluctuate into bits and pieces, as would happen with, let's say, with cylindrical micelles. And so we have these large entities that we might want to describe that are held together by bonds of the strength of, that's KT physics. We don't have any chemical bonds, but they're stable. And there's these large objects, and I would like to describe them efficiently as like entities of their own right. And so what I'm going to do today is figure out how to do that well. So in the second lecture, in our second lecture, the idea is to talk about lipid membrane elasticity. And I'm going to have this in 4 steps. The first thing I would like to say a few words about geometry, meaning we will have to figure out ways for how to describe these membranes in a way that's not focused on the lipids, but focused on the whole membrane as an entity. Having done this, we can then write a continuum theory for these objects, which is based on elasticity theory. And once we have that, we can start to ask meaningful questions about these objects, these elastic objects. One of the questions that I will address is, what kind of shape do they have? So given certain boundary conditions, what shape would they assume? And another question, bringing in KT, again, in closing the loop, is what can we say about fluctuations of these entities? So that's the path for today. Now, as a reminder again, so we have these lipid bilayers. And as we've seen, and Patricia has reminded us yesterday in lots of very, very beautiful pictures, they have a thickness which is molecular. It's like 2 molecules thick, which is on the order of 5 nanometers, 4 or 5 nanometers, depending a bit on the lipid. But their lateral extent can be anything between tens of nanometers to hundreds of micrometers. And so in particular for the large membranes, the aspect ratio between their lateral extent to their thickness is very large. In fact, an aspect ratio, even if you just have 10 microns to this, is like 4 orders of magnitude, and that's more extreme than paper. Okay, so they are laterally extend and just incredibly thin, and as such, it makes sense to think about these membranes as kind of surfaces that are embedded in 3-dimensional space at sufficiently large scale, right? If you look at 5 lipids next to each other, it's a terrible description, but if you look at large membranes, it's probably a good description. So that suggests we could describe membranes as 2D surfaces embedded in 3D space. So the first question for today is, how do we do that? And it turns out there's a lot of ways of how you can do that. I'll talk in detail about one. I'll briefly mention another one. And then we'll stick with the simple one, because almost anything I like to do today, I can do at the fairly simple level. But at a reasonably advanced and very broadly useful level, one way to just deduce is to say, okay, the way to describe this is to have to give coordinates on the surface to say where stuff are. And so since surfaces are two-dimensional, I need a two-dimensional coordinate system, let's say with coordinates u1 and u2. And I have some region in this coordinate space that will map onto a membrane in 3D. And so that membrane in 3D then lives in three-dimensional space, x, y, z. And I'm going to have to map this to something that's in 3D space, which then kind of looks like this. There's some potato chip there. There's a function which takes any point in this two-dimensional space and maps it to a point on the surface. And there's all kinds of conditions and smooth and yada yada. This is what's called an embedding function, x, that depends on u1 and u2. And clearly this can describe a very wide variety of surfaces. Now, originally when I just started to write my notes, lecture notes, I had very ambitious plans that I'm going to tell you a fair bit more about how to do this and how to describe the geometry and the areas and the curvatures and all of that within this parameterization. And then just when I just had my notes and started to figure out what do I actually put on the board, I realized, like, who am I kidding? I do not have the time to do that. But you have the notes. And so if you look at section 3.2.2 in my notes, you'll find a reasonably detailed beginning introduction as to what you would have to do there, what are some of the finicky things to pay attention to, and some of the basic formulas that will put you in a position to calculate the stuff that you would need without much of the noise of differential geometry, but it will open the door so that you can then look at more advanced treatments or just be able to read a differential geometry review that I wrote like 9 years ago or something like this that goes into more detail about this. It exists, very powerful. I'm not going to use it today. What I'm going to use today is a special case of this in some sense where I take that patch and move it right away into this XY base plane and just move it up. So a parameterization that looks like this. Okay, here's my three-dimensional space. That's X, Y, and Z. And I have some sort of surface that's sitting here. And it sits on top, right? Its reference surface in the base plane. And the way I describe this is by saying, okay, so I have a function that depends on x and y, where x and y are the coordinates here. So there's this point has an x coordinate here and a y coordinate here. And for every x, y down there in the region I care about, I tell you where the functional value is. So this is the most stupidest generalization of just plotting a function f of x. I give another dimension y and plot a function of f of x. Okay. This thingy here, this particular way of writing surfaces is called Monge gauge. And it has, it has the redeeming factor of being very simple and very intuitive. It has the downside that there's lots of surfaces you cannot describe like that. If you think about this, I think I have actually an example here. Assuming this makes up, will you wake up? Yes. We have two surfaces here that are somehow embedded in three-dimensional space. This is a surface that's very nicely accessible to Monge gauge. There's x, there's y, there's a function f of x and y, and there's some wavy kind of thing sitting there. But here's a surface where this is kind of a bit problematic because this surface has overhangs. So there's clearly points down here where this particular xy value has 1, 2, 3 points on that surface, and you can't just describe this by a single function. In this particular case, it turns out if you rotate this thing around y by 90 degrees, you can. So this is just a stupid choice of axis. But in general, you could imagine this doesn't always work. Okay, we're going to stick with situations where we can do that, which at the end of the day is a little bit less restrictive than you might think, because what's ultimately needed is not just to be able to describe one whole surface in one parameterization. What you anyways do is you take patches of the surface, there's lots of patches, and describe all of them in different parameterizations, and have to figure out if patches overlap. How do you make them agree? The lingo for this is that such a parameterization of surface or a piece of a surface is called a mapping. And in order to catch the whole surface, you probably need lots of mappings or lots of maps. Lots of maps are collected in what's called an atlas. And so you need an atlas to describe your surface. So anyways, the aim is never to just have one. But if you can get away with one for what you need to do, that's of course nice. And for today, we'll be able to get away with one. So we need this to be quantitative to say exactly where our surface is, but what is it that they then want to do with this? What we need to do in order to do physics is we need to describe geometric properties by geometric properties, I mean things such as length, area, curvature, or these things that describe the real existing geometry of the surface. We need to do this in such a way, that transcends coordinates. Coordinates are this awkward thing, but on the one hand, it's important to have them to describe anything precisely and quantitatively. On the other hand, they're completely arbitrary. It's your choice. So how can physics depend on your choice? Well, it can't. So you have to find a way to describe the things that are really existing properties of the surface in such a way that they become coordinate invariant, reparameterization invariant, or whatever. It's a big theme in physics to make things invariant of your particular description. So let me look at two things. One quickly and one with a little bit more effort for how to describe it. Ooh. The first is area. One of the things you could ask about the surface is like, how big is its area? And so the way to think about that is, well, conveniently move this away from me. Imagine you have a little rectangle down here. Where you dx dy, you know exactly how to calculate its area. It's dx times dy, done. But its image up there on the surface is some kind of weirdly tilted rectangle, which probably has a larger area. And so what is it? So a little rectangle dA naught, which is just dx dy in the base plane, has a larger area on the surface. What is it? And that larger area turns out to be, I'm just going to write it down and say a few words about it. That area turns out to be, dA is just dx dy times a factor that are going to make it larger. And that factor turns out to be, in Monge gauge, the square root of 1 plus the gradient of your function at that time, at that point, squared. So the question is, why is this true? Why? And here I'm going to be mean and say, well, there's a motivation that I encourage you to do that will make immediately a lot of sense and make this very happy for you, which is problem 1 in the notes. And if you actually want to prove it, there's many ways to do it. One particular proof is in problem 5 of that chapter, except the problem here is that you will need to know this section to be able to do it. But there's other ways of how to do it. It's not that mysterious if you just hit me up afterwards. I'm not going to say much about this because it's the relatively easy things. You just have to figure out, okay, what would the vectors look like that if you move them up, how long are they, and what's the area of a parallelogram with these vectors? It's not rocket science. The stuff that's going to take us longer to wrap our minds around is not area, but curvature. Because curvature turns out to take a bit more thinking about what we even mean by that. in the situation of a surface. So the idea here is that local geometric properties and the curvature is clearly a local property. Local geometric properties, in some sense, pop out of local expansions. So the time and true master weapon of physicists and mathematicians really is to Taylor expand the hell out of everything and figure out how much can we learn from Taylor coefficients at this point. Turns out a lot. So let's say we expand that function f of r around a point P, which sits in the base plane and has coordinates px and py. I'm going to write this expansion down up to second order, first in components and then in a slightly more concise vector notation. In components, it would just basically look like this. Okay, f of x and y is, okay, first of Taylor, right? We start at the expansion point, which is f of px and py. Plus, now it comes the first order term, which is, now since we have two dimensions, x and y, we have a sum, I from 1 to 2, df by dri. Ri is x and y. You need to evaluate this at the point P, because that's where we're expanding. And then you multiply it by the expansion distance, Ri minus Pi. And that's the linear term. And the quadratic term has, first of all, a 1/2. And then again, a sum. Now, of I and j, from 1 to 2, we have a second derivative, d to f by dri drj. These second derivatives, again, need to be evaluated at the point where I'm expanding. And now I have to multiply this with Ri minus Pi times Rj minus Pj. And then, of course, this higher order terms. Turns out we only have to go to second order. So that's one way to write it. There's a way to write it that's a little bit more compact in vector notation. We said that f at r is something like f at the point I'm expanding plus, and this first term, which is df by dri times ri minus p, looks a little bit like a scalar product, which is, of course, exactly what it is. It's the scalar product of the gradient of f evaluated at p times r minus p. Oh, yeah, I can try to write larger. Always the same. I'll write too small. R minus p. And the next term has again two vector differences like here, and something that looks like it has two indices that looks a bit like a matrix. So I can write this as a quadratic form, 1/2 p transpose times that matrix H times R minus P. That matrix H, again, is evaluated at P, is basically this object. It's called the Hessian. It's the collection of second-order derivatives of our function evaluated at that point. It's a symmetric matrix because these partial derivatives commute. And I'm multiplying it from the left and to the right by a vector and its transpose. So it's a quadratic form. And then there comes all the other stuff, plus da, 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 da. Well, we don't have to go as far for today. Good. So why are we doing this? Because these second derivatives are enticing. Right? These second derivative they smell like curvature. So are they? Would be nice, because then, okay, right, fine. The first order has the gradients give us the area. The second order is the Hessian gives us the curvature. Yay. We're in business, so let's check whether that works. And one way to check this is in a case that we probably understand a bit better, which is the 1D case. So let's specialize this to 1D. Specialize to 1D. Then we have, let's say, f of x is f of p plus f prime of p times x minus p plus f double prime of p, or half f double prime of p x minus p squared, and the Hessian just becomes a second derivative. And the question is this thingy here the curvature? Okay, of that curve at that point? And the answer is no. Sorry. And the simple way to convince yourself that that's the case is take an example. The function f of x is x squared. It's a parabola. If we take the second derivative, the first derivative is 2x, the second derivative is 2. So f prime prime of x is 2, which is a constant. If this were the curvature of our curve, then our curve would have to be a circle. But it's not. Our parabola is clearly not a circle, so that's, what's the technical term? Sad. That's sad. So, okay, what? There's a consolation prize, though. And the consolation prize is that it is the curvature if f prime of x is equal to 0. So at points of your surface that are horizontal, the second derivative is the curvature, as you might want to check. So it tells you that the curvature of a parabola at the origin is 2, so you have to put a circle there of curvature 2, radius of curvature I have, and see whether that would work. And it does. And there's another problem where you can convince yourself that that kind of works in the notes. But I mean, that just really kind of answers the question for the curve. For the surface, even if the surface is flat, that second derivative animal still is a matrix and not a number. So we have to figure out what we mean by curvature when we're actually staring at a matrix. So it turns out H indeed does describe the curvature at points where grad f vanishes, just like in the 1D case. But I do owe you a few more words on what I mean by describe. Okay. And so the way that this works is that reminder. So this is a matrix. It's a 2x2 matrix. The Hessian is not just any old 2x2 matrix. H is a symmetric 2x2 matrix. And because of that, it turns out, as you all know, it has two real eigenvalues and associated eigenvectors. And so if I look at the eigenvalue equation for this thing, if I write H times some eigenvector V, of course, we have two of those, VI, and those would be eigenvalues CI times VI. If I look at this problem, I know this works, it's a symmetric matrix. Then these eigenvectors have a particular meaning. This is what's called principal directions. And the associated eigenvalues, Ci, are called principal curvatures. And I'm going to show you in a minute with a picture of how to think about this. It also turns out, since this is an eigenvalue problem for a symmetric matrix, if the eigenvalues turn out to be not the same, if they're different, then we're guaranteed that the two principal directions are perpendicular. That's just true for these types of matrices. If they are the same, we're not guaranteed, but we can pick them to be orthogonal. We can always pick an orthonormal eigensystem for these matrices. And now you say, fine, now there are two directions in my surface where I know the curvature. Like if I go in this direction, but like if I cut my surface in this direction, then that cut turns this into a planar cutting curve, and I kind of know what I mean by curvature for a curve, that you fit a circle to this thing. But and I know this now in two directions. What about any other direction? And there's a nice theorem for this. So if V is an arbitrary direction, along the base spline, or just aim along the surface which direction, such that the angle between V and the first principal direction is phi, then the curvature along V can be expressed as a linear combination of these curvatures C1 and C2. In fact, it turns out to be cosine squared phi times C1 plus sine squared phi times C2. You realize that this goes back to what we said for phi equal to 0 and 90 degrees, but it's also true for anything in between. This thing is called the theorem of Euler, which is a bit weird because he apparently didn't yet have enough theorems named after him. And if you actually want to look it up and you Google Euler theorem, it's hard to find because the guy was good. But let me illustrate with a few pictures for how to think about this, right? And let me turn this on. So here's the surface. And I just picked something very simple, quadratic. So my surface f1 of x and y is a half x squared minus y squared. And it kind of looks like this kind of potato chip. I can calculate the Hessian of this. I have to do second derivative of this. So the second derivative with respect to x twice done, which is the upper right element, is just 1. 1/2 x squared twice differentiated with respect to x is 1. I get a -1 at the y term. And since if I differentiate it by x and then by y, I get 0, the off diagonals are 0. So this is actually not just a symmetric matrix. It's already diagonal, which means the x direction and the y direction is a principal direction. And the associated eigenvalues are 1 and -1. If you look at the surface, if you go along the x direction, you see this upwards pointing parabola, and you have a curvature +1. If you look at the y direction, you get a downwards pointing parabola with a curvature of -1. So the signs tell you up versus down, and these directions tell you, so how are these directions special? It turns out that these curvatures are like extremal. If you pick any direction, those are the largest or the smallest, whatever curvatures you can get. And the reason why they're extremal is because as these eigenvalues, they are the solutions of an extremal problem. And you get these largest curvatures, smallest curvatures, anything. So, okay, fine. We have an example where there's two obvious directions, the eigenvalues, and fine. Let me show you another example. Here's another surface. which is also kind of quadratic, but it looks like this, xy. If I calculate the Hessian for that, if I do two x derivatives, I clearly get 0. If I do two y derivatives, I clearly get 0. So on the diagonal, we now have zeros. If I differentiate first with respect to x, then what remains is y. If I now also differentiate with respect to y, I get 1. So I have a 1 here, and for symmetry reasons, I have another 1 here. So now the Hessian is still symmetric, but it's not diagonal. So now x and y are not the eigendirections. But it's not too hard to figure out what eigenvalues are. So what eigenvectors are. For instance, the vector 1, 1 is an eigenvector of this matrix. It's not normalized, but doesn't have to be. So that's a direction, that's an eigendirection. This one here, 1 minus 1, is also an eigenvector, and it's perpendicular on this one. If I work out what the eigenvalues are, if I just take this matrix and multiply it by this, I just get 1. So the eigenvalue here is 1. If I take that matrix multiplied by this, I get this thing back with a minus 1. And so the eigenvalue here is minus 1. So I get the same principal curvatures, 1 and minus 1, but very different principal directions. So looking at this thing, along the x direction, for instance, the surface seems flat. Along the y direction, the surface seems flat. But along the 1, 1 direction, which is here, I indeed again curve up with curvature 1. And on the 1 minus 1 direction, I curve down. Okay? And these are the largest curvatures and the smallest curvatures I have. Okay? So this is an example for how this would work out. It also turns out to be an example of how coordinates, as useful as they are very arbitrary, because these two surfaces are the same surface. It just happens to be that this one is this one rotated by 45 degrees. It's not obvious at all if you look at these functions, because the parameterizations look very different, but the surface is the same. And as a geometric object, it shouldn't change if I just move it around and tilt it and rotate it. And so that means part of our task that we still have to do is figure out how to work with these things in a way that the arbitrariness of this parameterization doesn't infest all the physics that we later wanted to do. We made a big step in the right directions because the eigenvalues, the set of eigenvalues was the same. So the local curvature properties are the same. They're just oriented in a weird way. I don't care about the orientation. Okay? So that's good news. We're clearly on the right track with this. Good. So let me now drive these points home with by just writing a note. The eigenvalues which seem to be enticing things to look at if you want to just shed parameterization, the eigenvalues themselves are not reparameterization invariant. Well, proof, in this case, we had eigenvalues 1 and minus 1. If I take my surface and I rotate it by 90 degrees, then the 1 eigenvalue becomes minus 1 and the minus 1 becomes plus 1. So they swap place. So they change. So that's not a good idea to use individual eigenvalues as if they have physical meaning, because they still depend on your choice of axis. Swap coordinates, swap the eigenvalues. But certain combinations of them are reparameterization invariant. And the ones that we will have to deal with, because they're turned out to be useful at the level that we care, are the sum of these eigenvalues, something that's called the trace, which is C1 plus C2. It's the trace of the Hessian, and the trace of the Hessian is parameterization invariant. And the other one is their product, which is the determinant of the Hessian. C1 times C2. For things that you've probably learned in linear algebra, things such as traces and determinants are invariant under a change of coordinates. And so these are nice geometric objects because they do not change if you change your coordinates. And so they've been given particular names. Curvature-wise, the C1 plus C2 is something it's called the curvature or the total curvature. Some people find it very useful and divide that by 2 and then call it the mean curvature. It's fair, but in my entire life of doing this, I've never found that factor 1/2 useful. So I always talk about the whole thing. The C1 times C2 is called the Gaussian curvature. Clearly because Mr. Gauss himself didn't have enough named after him. But to be fair, he did an awful lot of important work exactly on this field, so I guess he deserves his name there. Question, where was the question? There, please, yes. There's only 2.
So like is the list C1, C2 also invariant? Like
oh yeah, okay. So the only thing which happens is swap their order at this point. Yes. Good. Where are we? Okay, so and to conclude that part, so that's nice. We figured out a way to describe the local geometry curvature-wise in a way that shed all the remnants of parameterizations. And we know how to calculate these things. Expand, calculate the well, how do we know how to calculate this? Because I thought this only works, the whole Hessian thing, if your surface is flat at that point. What if it's not? What if f of x and y is not horizontal at the point you care? You might still want to know what the curvature at this point is. I'll give you 3 options for what to do. The first option is, before you do all the derivatives, I just rotate the surface until you're flat, and then do your derivatives. That sounds easy when I say it in words. In practice, rotating something in Monge is not at all easy, so that's a bit annoying. But at least in principle, if you have a weird surface in real life that you need to describe, just don't randomly describe it. Orient it first before you describe it in such a way that the points you care about are nice. Okay. The other solution is work out the thing a bit more carefully, work with a more complicated formula. And the more complicated formula for this one here, I should say, these also get names. The total curvature I'm going to call J, and the Gaussian curvature I'm going to call K. And so there's a nice formula for J, which works like this. So in some sense, we would like to back up. So trace of the Hessian, what is this? It's d to f by the x squared plus d to f by the y squared. That's the Laplacian of f. So the Laplacian is the curvature if the thing is flat. What if it's not? Well, then you take not the divergence of the gradient, but the divergence of the gradient, which is first normalized in a funny way by that other mystery factor, 1 plus grad f squared. This expression is the curvature even if the thing's not flat. And notice that if it's not flat, then this thing cuts this down a little bit before you differentiate. And if this is 0, we go back to the Laplacian. I should also make another comment, which is about the total curvature has a sign convention problem, which is if you look at the surface, you look at this point, and you bend it like this, and it says, all right, is this a positive curvature or is this a negative curvature? Hands up who thinks this is a positive curvature. Hands up who thinks this is a negative curvature. All right, so 60% of you have no opinion on that. That's okay. The thing is, look, I can do the following thing with the surface without changing it. All right, so has this point a positive? Okay, so you get the point. It's arbitrary. Of course, this thing will answer the question, but I have to make a completely arbitrary choice at this point. The completely arbitrary choice that I will make, if I may steal was something yellow from here. The completely arbitrary choice that I will make is that I angle in one more minus sign here, convention Deserno, if you like, but lots of physicists are with me on that one. And the reason is, if you describe this f of x and y and you do like this, it's bending down, so the second derivative is negative, but I put another minus sign in front of this. This has a positive curvature. So if you stand on a hill and everything goes around down, you're at a positive curvature. If you stand in a valley, it's negative curvature. I just like the idea that a sphere has a positive curvature. So when I stand on it, and so that's what this minus sign does. But it's a complete convention, which means someone else might use a different convention and then not tell you about it. And then you're screwed if you try to find minus sign. The same problem does not occur with K, because any arbitrariness in the sign of C1 comes back in the sign of C2, and then it cancels. So K, the sign of K is uniquely meaningful. The sign of J is a convention that you just got to pick and then stick with it. That's a question.
Quantities here, the trace and determinant, are
yes.
Under like basis.
Yes.
So if I did something nonlinear, like moving to spherical coordinates.
Well, then things are more complicated.
Right. But, okay. So this isn't like an intrinsic, like a covariant description of your curvature.
It is still a covariant description. So invariant always means under what kind of things. All I showed you here in Monge gauge is if you do rotations and stuff like this. And it's in the third point that you can do, which is use chapter 3.2.2, you will also discover that you can define things which is generalization of the Hessian, which is a curvature tensor, and this multiplied with an inverse metric and traced over will give you that. And this is covariant in the sense it's invariant under any diffeomorphisms that you could pick. So that's very powerful because you can pick any coordinates on your surface, nonlinear transformations, whatever. Your curvatures do not depend on that, right? But for that, you have to go onto that level because if you go beyond rotations and Cartesian stuff, then the whole co- and contravariant stuff hits you. And so you got to be more careful. Okay, good. That was the geometry side of the story. So now we know how to describe surfaces, and if push comes to shove, we can calculate their curvatures more or less easily. What do we do with this? Well, I said the goal was to describe things that are. What is this thing? I'm getting so confused about all these. There's one right in the back, or not? How do I get to this one? Okay, I'm losing precious minutes here, but okay. One board short now, cool. What could go wrong? The reason why we did all this is we would like to describe membranes as surfaces and then put some physics on it. All we've done so far is geometry. We would like to do some physics. So, and the physics I would like to do is elasticity. So I would like to describe how am I doing in time. Probably terrible. Yes. I like to take a surface and deform it in a funny way and figure out what the energy is. The easy bit is stretching the surface, because then I don't even need to bend it. I can just flat surface, make it bigger. And we've already seen what the formula for this is. A stretching energy is something like 1/2 and some spring constant, which I'm going to call Ka, times the square of the strain, which is the area that the surface has minus the area that it has if I didn't pull on it, squared. And I normalize it by A0, so that this has dimensions of area times this modulus gets you to stretching energy. This is just Hooke's law. It's a quadratic function, which you can see by saying, okay, the stress in the system, sigma, is the derivative of that energy by the area, and you get Ka times A minus A naught over A naught. A minus A naught over A naught is the relative change in area, so that's the area strain. And this is the stress. And what this equation says is that the stress is proportional to the strain, and that's Hooke's law. And the modulus here is the area stretching modulus, and Patricia already talked about it yesterday. It usually for lipid membranes has usually values on the order of 250 millinewton per meter. And that's the easy bit of elasticity, and I leave it at that. The hard bit of elasticity is curvature, of course. So how do we do that? Actually, now that we have all the geometry at our disposal, it turns out not to be so hard after all. So, to the difficult bit. Bending. So now the idea is that we can locally expand our energy in powers of geometric invariance that use higher and higher derivatives of these functions. For instance, second derivatives go all the way to curvatures. And so a bending energy density would then look like, okay, the lowest order term is just a constant, has nothing to do with the shape. And then the first order term I could write is the curvature, C1 times the curvature. And so that's linear in curvature. I could also go quadratic in curvature by saying, okay, so how about another term, C2 J squared? Okay, that's quadratic in curvature. But then you realize, oh, at quadratic curvature order, I have another term that I could write, which is C3 times K, because K is quadratic in curvature, it's the product of two of these C's. C is, those C's are not the curvature C's, I apologize. That J is linear in curvatures, so that's quadratic in curvatures. That's already quadratic in curvature. So anything after that is going to be cubic, and so I'm going to stop at this point. I'm just going to find an expansion that is just goes all the way up to quadratic order in curvature. I should also say, remember that I said that the sign of J is arbitrary? That means we have one term in here that seems to have an arbitrary sign. That doesn't seem physical, that there's somebody changes their opinion on where the normal vector goes and boof, the energy changes. Well, it does make sense though, because I said this is the same thing as that, only if the two sides are the same, right? If this side is red and this side is blue, then blue side out versus red side out is not the same surface. And so now there is a meaning to this sign of J. And so if the surface does not have up-down symmetry, this term is allowed. Conversely, if the surface has up-down symmetry, there's no reason why this term should be there. So that means this term can only arise, or can only be there, if the up-down symmetry is broken. And then it's there, otherwise it has to be zero. Now it turns out people don't like to write the energy like that. It's not very telling. So there's a nicer way people have decided to write this by sort of renaming coefficients. The way to write this is to not call this C naught, but to call this sigma, and to combine this term, and in some sense this one, into something that looks like this, plus a half kappa J minus J naught squared plus kappa bar K plus da da da. You realize if you square this out, you basically get all the same terms here, so you can relate the constants to each other if you want to. And you realize that this thingy here, the J naught, has the same iffiness as the C1 in the first line. It can only be there if up-down symmetry is broken, because this creates a linear term in J, which is only physical if it makes sense to talk about the sign of that curvature. So these constants then are called, this is something like surface tension. We'll get to, surface tension is the worst concept in this whole thing. This is what's called a bending modulus. This is what's called a Gaussian curvature modulus because it multiplies the Gaussian curvature. Question? Well, it's the J is, okay, it's the sum and the product of the things that have meaning, which is the eigenvalues of the Hessian, right? Yes. Yeah, let me see if I can do this on top of my head. Same J, different case. Sphere has some mean curvature. So it has if this sphere has radius r, then J is 1 over r plus 1 over r, which is 2 over r, while the Gaussian curvature is 1 over r times 1 over r, which is 1 over r squared. Okay, if you take a cylinder and give that cylinder a radius that I'm just going to call r over 2, then the mean curvature is 1 over r over 2 plus the other curvature in this direction is 0 because it's flat. So it's 2r, the same as the sphere. But the Gaussian curvature is 1 over r half times 0. And so it's 0. So these two objects have the same mean curvature or same total curvature, but they differ in Gaussian curvature. Okay. And so what we have here is the energy per little area element dA on the surface. So the total energy of a whole membrane, which now depends on the whole surface, E, which depends on the surface, S like surface or like shape, would then be an integral over this entire surface. We have to integrate over the surface, so that dA is the more fancy area element on the surface, which looks potentially funny. dA times this expression, sigma plus a half kappa J minus J naught squared plus kappa bar K. And we're going to stop it here. And this expression is the glorious, wonderful, studied to death since 50 years, Hessian Hamiltonian. And I'm going to spend some time talking about what this means in terms of what shapes would a surface like to take whose energy is described by this. And if this surface is embedded in a fluctuating environment and it starts to wobble, we've seen this beautiful picture of a wobbling giant vesicle yesterday, the movie by Patricia. What can we say about these wobblings? Okay, cool. There's a few comments that I would like to make. I'm probably not going to write them down, but they're in the script anyways. The first comment is that the Gaussian part, this kappa bar times K, turns out you can very often ignore that. But you can ignore it for a curious reason. It's not because it's small. This term is very much not small. It typically is of the same order of magnitude as the other term. So why should I be able to throw it away? The reason is because there's some curious bit of differential geometry magic that's called the Gauss-Bonnet theorem. And the Gauss-Bonnet theorem tells you if you have a surface and everywhere you calculate on the surface what the Gaussian curvature is, and then you integrate that over the entire surface. So exactly where we have the integral dA k, that kappa bar is just a constant. The resulting answer turns out to depend on only two things. The first is some wicked properties at the boundary of the surface, something it's called the geodesic curvature, and something that only depends on the topology of the surface. And it turns out very often for the kind of things you do, neither the boundary changes, or maybe the surface doesn't even have a boundary, nor the topology. And then for the kind of deformations of the surface you care about, the Gaussian term never changes because it's an invariant. And so it doesn't matter whether its value is 50 bazillion joules. If it's 50 bazillion joules before you deform the surface and after you deform the surface, the change in energy is 0. So you don't care. That has good news and bad news. The good news is you can almost always throw it out and ignore it, so that's one parameter less to worry about, kappa bar. The bad news is sometimes it does matter. And then you have to know it. And then you have to measure kappa bar. And then you're very restricted by the kind of things you can do to actually affect that term, boundaries and topology. Both of them are hard. So that gets you into problems. Okay. So, yes. You can, if you, so this is a quadratic in a curvatures. If I write this as a quadratic form in C1 and C2, one thing that I need to be true is that this quadratic form is bounded below, so that the energy cannot, by some clever choice of bending, go to -infinity. So that matrix has to be positive semi-definite, and that puts conditions on kappa and kappa bar, so that kappa bar has to be between 0 and -2 kappa. Kappa always is positive, so -2 kappa is negative, and between -2 kappa and 0, that's where kappa bar has to be, otherwise your surface is not stable. And that order of magnitude-wise means they have to be roughly there. Oh, don't get me there. That would be a whole talk. Sorry. One final thing is, since I gave you Monge, and there's no Monge left. Sometimes, if you want to do calculation, we have to go back to Monge, in particular to a linearized version of it. So if the surface S is in Monge gauge, and we can expand to quadratic order. In F. And we set J0 to 0 for symmetric membranes. Then this expression simplifies to E bending is approximately an integral, which I now do over the base plane, dx and dy, not over the surface, but over the base plane, x and y, base plane, over two terms. The area term is just the sigma times the area. The area was square root of 1 plus grad squared. I expand this square root, and that will give me a sigma times grad f squared. And I take the curvature term, and I expand the curvature formula up to quadratic order. Then all the non-flatness will go away as a complication, and I will get plus a half kappa Laplacian of f squared, and that's it. So this is the Linearized Hamiltonian in what's called linearized Monge gauge. And it seems it's very specialized, but it's probably the version of the Hamiltonian you're going to find out most, or probably 90% of all the paper do anything with these things, work with this. And it's not baby, it's still interesting. So there's good physics coming out of this. And I will, for the rest of today, restrict to this because it's easier. Yes. Yes, absolutely. Quadratic order and F expansion means I have to assume something is small. What is small is grad F. So this is equivalent to assuming this. Okay, so we have now an expression for the elastic energy of a surface subject to some surface tension and subject to some bending rigidity. And we can now ask questions. What shapes would these surfaces like to take if I squeeze them from these directions?
The triangle that points up.
This one, that's the Laplacian. That's a weird equation, but it's true. Okay, cool. So the question is, if that's the energy, what shape would a surface like to take? So let me talk about this. Let me ask something about the shape equation. which says what choice f of x and y would minimize this function so that the energy is smallest. The way to do this, of course, as many of you know, is to do functional variation. Where you write your shape f as some optimal solution f star, which is like the idealized perfect shape, plus a little wiggling around it. And that wiggling is not just a little shift up or shift down, that's a wiggle that's position dependent. So you take your surface and wiggle it into something else. And you will probably have seen how to do that. So I'll still do a little bit about it in an abbreviated fashion. But the reason why I do that is because I want to spend a little bit more time than usually done on what's called the boundary terms. Because they are interesting, and apparently all other derivations tend to hate the boundary terms, which always grates on me. So let's do it properly. And to do though, let me do this in 2 steps. One explicitly, and the other one I wave my hands. This energy has 2 parts, the sigma part and the kappa part. Let me just start with the sigma part. So how does the energy per unit area change if I wiggle the sigma part? Well, what that is a half sigma times grad f squared, and f is now that f star plus delta f. So this is grad f star plus grad delta f squared. And since I want to change, I have to subtract out 1/2 sigma grad f star squared. So we have to calculate that. And we only, since we wiggle small, I'm going to only expand this up to linear order in delta. So if you square this out, the first term is 1/2 sigma delta f star squared, which is exactly what I'm subtracting out here. That goes away. The next term is going to be sigma, the cross term, sigma grad f star, scalar multiplied into grad delta f. And then the other term is 1/2 sigma grad delta f squared. But that's quadratic order, so I'm going to ignore it, plus a higher order term that I don't care about. The idea here really is, if I am at a minimum and I wiggle around, then to linear order, nothing changes. That's the same. You have a parabola, you're in the minimum, you wiggle around a little bit on the x, and the y to linear order doesn't change. I want to figure out how can I make this thing to linear order in my wiggling not change. Okay? But what I'm going to do is I'm going to rewrite this a little bit, but because I don't like the fact that my wiggling has a derivative hanging on it, I'm going to remove the derivative. The way to do so is to say, well, how about I differentiate the whole thing? Take the divergence of grad f delta f. Then I have the derivative out, and there's no derivative left here. So yeah, that's fine, but that's not the same. If I do a product rule on this, I get grad f delta f star, so that's the one I have, but I also get one that has 2 derivatives on f star. So this I have to subtract out. Minus sigma divergence grad f star delta f. And this is again the upside triangle. So this is just a rewriting. But I rewrote my first order variation of whatever is in this integral as one term, that's a total derivative, and one term that it's not a total derivative, but the delta f, the wiggling, has no more any derivatives hanging on it. So that's nice. And the reason why this is nice is because integrals over total derivatives tend to be nice. I can push that to the boundary by Stokes' theorem. And I have to do the same shenanigans for the second term. For the second term, it's a bit harder because there's 2 derivatives hanging on f. So there will be 2 derivatives hanging on delta f. So I need to do this unburying twice. But OK, it's just a little bit more work. And if you do so, and you use Stokes' theorem, which says that the integral dx dy of something like the divergence of some vector field, we're going to do this over some region R, then by Stokes, this is equal to the boundary integral over the boundary of that region. The S is the arc length element along the boundary, some vector L dot V, where this is the outward pointing unit normal. Okay? And using this theorem and using all of this unpacking it and then throwing integrals on this, the total change in energy of my bending energy of my surface can then be written as the following thing. One is the integral dx dy over whatever region I worked with, which contains now all the terms which don't have any total derivatives, which have only these things, and multiplied by delta f. These terms look like this. Kappa, Laplacian, another Laplacian on f star minus sigma Laplacian f star. And all of this multiplied by delta f. This minus sigma delta f star delta f is exactly this. Minus sigma delta f star delta f. Here it is. The other one with two deltas is because if I have two Laplacians on the delta f and I just shuffle them off and I put them onto f star, I end up with another Laplacian on f star, so I get four derivatives on f star. But this is only the stuff that revolves this term. What about these terms? I have a whole bunch of divergence this times this stuff, okay?
Yeah, just a comment. I'm surprised you're calling the whole thing bend, but the curvature is bending, but the other thing is a surface.
Fair enough. The whole Hamiltonian, that bending, tangent, everything together.
Cost.
This is not a horizontally applied thing. This thing is so fraught with complications. I like to think of it as a boundary condition that just tells me how much is pulling. Yeah. Okay. So, but we get these terms, and these terms by Stokes can be written as an integral of the boundary of whatever region that I'm working with, ds L dot stuff. And the L dot, all the vectors are there because the F's are not vectors. All the vectors come from the Laplace, from the gradients. So L dot a gradient gives me an outward pointing derivative. And so this thing is going to look like this. At first sight, it's going to look nasty. So it's sigma grad perp, which is that L dot grad, minus kappa grad perp Laplacian f star, and all of this multiplied by delta f. I should collect my delta f's here a bit more nicely. But we're not done. There's another term, plus kappa Laplacian f star grad f. And now we're done. So, and probably whenever you have seen things such as this, did I forget something?
Just the f star, maybe on the first term.
Yes, absolutely. Eagle eye. Thank you. Good. When people do these derivations in textbooks, in papers, so you typically only see this, and then they say, well, and the boundary terms will probably vanish. Which is not, I understand why they don't write it down, because this looks scary. But will these things automatically vanish? No, they will not. We have to make sure they vanish. Okay? So by the way, the idea, of course, is that we want to set this to 0, because at the minimum, at the optimal point, no variation, no change in energy. And so this is in the interior of my surface. This is on the boundary. Variations here are different from variations here. I can vary this without varying this and the other way around. So these have to vanish independently. This has to go away. This has to go away. So this is two very different things. And of course, on the boundary, changing of where the function is and changing what slope it has is also two different things. So those are two different conditions. And all of these things have to vanish independently. So let me see what that implies. So the first thing is, oh, here's all the yellow stuff accumulates. Okay. Within R, Making this vanish within R means making the first integral vanish. That first integral is integral dx dy, yada, 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 times delta f. Delta f can be anything you want it to be. The only way that that integral will reliably vanish is the yada, 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 yada is 0. Okay? There's a better proof to this, but we're good for now. And so setting this to 0 tells you that kappa delta delta f star minus sigma delta f star is 0. That's a differential equation. And this differential equation has to be solved, and it's the shape equation. That's the thing you would want to solve. It's the shape equation. This is the equation that determines the shape. It's partial, because these are partial derivatives. It's fourth order, because delta delta. And it's linear, because there's an f here and there's an f here. The first two are generically true for these kind of problems. The second, that this is linear, is a major simplification, because I use this quadratic expansion linear Monge gate. In general, this thing is not a linear differential equation if you just look at funny, weirdly shaped surfaces outside of Monge gate. But then you have partial, fourth order, nonlinear. What do we do? Nobody knows. Numerics. Okay, these are incredibly hard. And I will leave it at that. By the way, it turns out that a nice way of rewriting this is to factor out some of the deltas and write this as, first of all, there's a kappa here, there's a sigma here. Let me define a beautiful length that will come up later. Lambda as the square root of kappa over sigma. It's a characteristic length in your system once tangent and bending rigidity is set. And using that lambda, I can rewrite this as delta minus lambda to the minus 2 delta f star equal to 0. What that tells you, for instance, is that functions f whose Laplacian is 0, which are called harmonic functions, will solve this differential equation. I can also swap these two things around because these two operators commute. Functions where if I apply the Laplacian on it, reproduce themselves with a prefactor of lambda to the minus 2, which means eigenfunctions of Laplacian with eigenvalue lambda minus 2 are also solutions. So that's actually nice. I decoupled this thing into two second-order differential equations rather than one fourth order. Yeah, which is good. Okay, but we have a differential equation now. We have to solve them as fourth-order differential equations. They have lots of boundary conditions. Where do the boundary conditions come from? They come from here. That's why it's terrible that people just don't talk about it. But this is where the boundary condition comes. So let's think about this. This term has to be 0. This lives at the boundary, which means it gives you a condition at the boundary. Also, it says, well, here's the wiggling that I can do. Here's the wiggling that I can do. This wiggling is independent of that wiggling because the position of the surface at the boundary and the slope of the surface at the boundary, I can independently change. Okay, so this term has to vanish and this term has to vanish independently at every point on the boundary. And this gives me on delta r, on dr, gives me conditions that you could write down like this. There's two things that have to vanish. That gives you two conditions. A first condition and a second condition. The first condition comes from here. How can we make this vanish? Well, one easy way to vanish is if the delta f is 0, then, okay, that term is gone. Delta f is the variation of the height of the function at the boundary. What would prevent me from wiggling it around? What would prevent me from wiggling it around is if I happen to know that the surface at the boundary has to go to some particular location, because that's physically known to be true, it goes there. So if I know it goes there, then my trying of all the possible shapes, I'm not allowed to wiggle it at that point because it's fixed. So one way to make this vanish is delta f is equal to 0, and that means you fix f star at the boundary. That's one way to make that term vanish. But what if you don't know where the surface is at the boundary? So you do not know, the surface hangs somewhere there, and it can hang like this, or it can hang like this. You don't know exactly where it is. How do you now make that term vanish? Because if you don't know where the boundary is, you better try out all locations. And so delta f is not 0. Well, then
the other case. You have a way to solve the two parts separately.
This and this independently?
Already, so first line here, you already have a shape equation. So why don't you use shape equation after that?
Well, I need boundary conditions on the shape equation. The shape equations comes with constants of integration that I don't know, that are only determined by the boundary conditions. This lives in the bulk, the whole surface, and this is what is true at the edges of the surface. I need to make extra conditions there. Good. So if delta f, if I'm allowed to vary the surface at the edges, because I don't know what it does there, so I have to. This is not zero. But then I have to set this equal to 0, and now I'm good. And that gives me a condition at the boundary, which says that apparently sigma times the normal derivative of that function f star. Where am I? Can't see this. Minus kappa gradient perp Laplacian f star is 0. So that's the alternative. So you can either fix the position of the surface or fix some funny derivatives at the surface. That might remind you mildly of something you've heard in E&M when you solve Maxwell's equations or Poisson's equation in boundary. Then something like this, just fix the value, is what's called a Dirichlet condition. And this thing is called a Neumann condition. You have to pick one of them, not both, of course. You've picked one, but that's what you do. But that's only the first condition. That's the second condition, right? Same argument here. Either this is 0, because I'm not allowed to change the slope of the surface at the edge, because something sets it there. So it's fixed. So if you fix the gradient perp of f star, no, not the perp, fix grad f star, and that will guarantee a proper boundary condition. Or if you don't know what the slope is, the slope can change. You have to set Laplacian f star to 0 at the boundary. And everywhere on the boundary, you have to apply these two conditions, and among those, you pick one. Well, I'm fixing. Well, that's the Neumann version here. The Neumann versus boundary comes from the condition, not whether there is a derivative or not. It comes from, does it come from the point of view that the variation is fixed or free? That's sort of the terminology here. You would say, this is a Dirichlet condition, and all of those are Neumann condition. It's not the right way to think about those, because for this case and for this case, you have to pick either this or that. And here you have to pick either this or that. You can even pick differently on different parts of the surface, but you have to pick one or the other. To pick Dirichlet, I have to pick Neumann. Okay, cool. This maybe, yeah. Right. Okay, cool. The script walks you through an example, a fairly straightforward example for how to solve this in the one-dimensional case, which I thought I'm going to walk through, but only 15 minutes left. So I urge you to read the script. Instead, I would like to use these 15 remaining minutes to say something that Patricia already alluded to, and which is important for one of the homework problems that I hope you will do, which is fluctuations. And that's, in fact, experimentally very, very relevant. So we have these surfaces, and they can bend. And the bending rigidity turns out to be something like between 20 and 30 kT typically, which is larger than thermal energy, but also these surfaces are large. And so it turns out that under in a thermally fluctuating environment, these surfaces wobble around. You've seen this, again, I remind you, you've seen this beautiful movie that Patricia showed about a vesicle in solution that was just wobbling, or I think the proper term is flickering. There's flickering motions you can see with these things. And clearly, first of all, it's interesting to know how much these things flicker. And it turns out being precise about this will tell you something about the surface itself, because it's not hard to guess that if the surface is very soft, if kappa is a small number, it will fluctuate more than if kappa is very large and it's a very rigid surface. It will only do like wing, 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 as opposed to wop, wop, wop. And so by being quantitative about the extent of these fluctuations, you might be able to learn about the rigidity of the surface without actually having to bend it or something. So I'm going to show you how that works. It's a pretty neat, yes.
Even at the bottom of the top board,
Yes.
term,
Yes.
I don't understand what a gradient means. Isn't it a dot? It must be dot into it.
Well, this is a scalar.
No, but a gradient is a vector, and so you integrate it with the boundary. It has to be
Oh, yes. What happens there?
Also perp.
It should probably also be a perp. You're right. You're right. Thank you. So, right. So I would like to describe how to be quantitative about these membranes doing things, okay? And the way to do so is to, again, restrict to cases where this calculation can actually be done relatively easily. And it can be done relatively easily when the surfaces deviate only weakly from simple shapes, such as you have a sphere and it wobbles a little bit around the sphere. I'm going to look at the even simpler case if it's flat and it wobbles a little bit around flat. That's, in fact, the far most common case that people do in simulations when they simulate a membrane and it wobbles in your simulation box. You can quantify the wobbling spectrum, okay, the power spectrum of surface undulations, and measure the rigidity of something. Your model that nature doesn't tell you what it is. You can measure it that way. And so that's the situation that I will look at. I would say I will take a membrane on a square, how do you call it, patch. I'm going to call that just square patch, which is 0 to L squared. So this is your boundary conditions, subject to boundary conditions. In simulations, that's the most natural thing to do. In experiments, that's of course not a natural thing to do, but for sufficiently large systems, the boundary conditions are not going to be that important, so it's an okay assumption to put on the surface. I mean, the alternative, just pinning it somewhere, is equally likely not true for the membranes you're looking at. And so you have your surface, f of x and y, on that patch, and what we're going to do is we're going to Fourier expand it. So I'm going to write the surface f of r as a sum over Fourier modes q, Fourier coefficients f tilde of q, and e to the iqr. To be precise, so what are these q's? The Fourier modes q are, of course, 2 pi over L times nx and ny. Nx and ny come from the integers. And there's one more condition I need to be careful about, which is this is a real function. And because it's so much nicer to work with complex exponentials than with sine and cosine, I'm going to put an e to the iqr here. But I really still want this to be a real function. So I have to have conditions on the f's. And these conditions are that the Fourier expansion coefficient of a negative q is the same as the Fourier coefficient of the positive q complex conjugate. If you plug that in, you can realize by combining a q and a minus q, they add up to something that's real. Okay. So we're going to take this ansatz for f, which is just obviously periodic boundary, and it wobbles depending on what the fq's are, and I chuck it into our Hamiltonian, which is the one somewhere here. Where's my Hamiltonian? This one up there, okay? The linear of the quadratic expansion of Monge. It gets the terms here, and there's a term here. Let me only really explicitly do the surface tension term, because the other one is exactly identical. So I have to work out what is the integral over my square patch dx dy of Laplace of grad f squared. Of grad f. So what is that? Grad f squared. This is the integral dx dy over that patch. So grad f is the grad of this. So I have a grad of a sum over q e to the iqr. Sorry, f tilde q e to the IQR. That's one of them. And I need another one. Grad sum of, but be careful using a different summation variable, q prime, f tilde q prime e to the I q prime dot r. Okay, so this I have to evaluate. Okay, so the way to do though is to first let that act on here. So the grad of e to the IQR is IQ times e to the IQR. So you get integral dx dy sum over q IQ e to the IQR. And keep forgetting the modes. F tilde q e to the IQR times the sum over q prime I q prime f tilde q prime e to the I q prime dot r. Looks all very nasty, but it will simplify rather quickly. I'm now going to swap all the sums and the integrals, and I write this as a sum over both q and q prime. What else can I move out? I can move these q outs. I times I is -1, so I get minus q dot q prime. I get an f tilde q f tilde q prime, and then comes the integral, and the integral dx dy over my patch goes over e to the I q plus q prime dot r. All right, that was, so far it was pretty straightforward. Run for my yellow chalks. And now comes the beautiful thing, which is that Fourier modes are orthogonal, which means that this thing here is very easy. If it turns out that q and q prime are just negatives of each other, then q plus q prime is 0. So e to the 0 is 1. I just integrate the patch. I get L squared. But if q and q prime are such that q plus q prime is just another wave vector, then because of the fact that these are all multiple integers of multiple waves in the box, I'm ending up integrating an integer number of modes over the box in both x and y direction, and an integer number of sine waves integrated gives 0. And so this is L squared, Kronecker delta of q and minus q prime. This will only give you something if q and q prime add up to 0. And as a Kronecker delta, then, that kills one of these sums. I can get rid of the q prime sum and then picking q prime is equal to minus q. And so then this turns out to be a single sum over q. Q prime is minus q, so minus q dot q prime is just q squared. This q prime turns into a minus q, but f tilde of minus q is this f tilde of q star. And that multiplied by f tilde of q gives you f tilde of q modulo squared. And we're done. So this is what happens to this term. This is this term in real space. This is the term in Fourier space. The grad turns into 2 factors of q. And we can do exactly the same thing with a Laplacian, except that instead of grad e to the IQR, we get Laplacian e to the IQR, which gives us a minus q squared. And so everything together turns out that our bending energy in Fourier space now looks like this. It's L squared, and there's a 1/2, and it's the sum over all the q's. And there's an f tilde q modulus squared. And from the grad square term, I get a sigma times this, so sigma q squared. And you will hopefully not be surprised that from the Laplacian term, I get a kappa times a q4. Because the Laplacian gives you 2 derivatives. I have 2 of these in there. So 4 derivatives, 4 factors of q, q to the 4. And so this is the bending energy in Fourier space. It's just the same thing that was over there, just in Fourier space. But in Fourier space, it looks extremely nice. It looks extremely nice because every single Fourier mode Q really only appears in one term. There's no coupling of like FQ1 times FQ2 or something like this. All these terms are nicely decoupled. So this is diagonal in Fourier space. It was not in real space because the gradients always mix things left and right. Here, it's diagonal, super nice. And it's quadratic in our amplitudes of our modes, which means this is a harmonic oscillator. In fact, this is a sum of harmonic oscillators. In fact, it's a sum of independent harmonic oscillators. Nothing is easier than that from a Stadtmech point of view. All I'm going to do now is I'm going to use something that's called the equipartition theorem, which says if you have in Stadtmech a term that looks like 1/2 and a spring constant and some degree of freedom squared, and that's the only way that that degree of freedom occurs in your Hamiltonian, then the canonical expectation value of this in the canonical sum is just 1/2 kT. That's the equipartition theorem. And so you can solve this for the mean squared amplitude of this thing. It's going to be kT over the spring constant. So here the spring constant is everything in this expression for any fixed q that's not a 1/2 and not an FQ modulus squared. So the L squared, sigma q squared plus kappa q to the 4 is your spring constant. And so what we find is that F tilde q modulus squared, thermal average of this. What's the mean squared amplitude of a given Fourier mode of my membrane? This is kT, because it's excited by kT, divided by L squared, kappa q to the 4, plus sigma q to the squared. And that's the power spectrum of thermal shape fluctuations of a Helfrich membrane. And clearly, if you can measure this, and people, all you need to do is look. It's a bit harder than that. Sorry. You look and you measure the shape, you Fourier expand the shape, you do statistics over this, you measure this thing, and then somebody says to you, well, this is the function it should look like. You fit this function, you know kT, this has to be put into the normalization, and out of this pops both sigma and kappa. So you can measure the tension and the bending rigidity by fitting to the spectrum. Yes? Okay. Right. So this goes back to a comment I made yesterday to somebody sitting over there. In Stadtmech, you always have a Hamiltonian that describes the energy, and then you throw thermal fluctuations on it, and then it fluctuates. He says, well, you didn't have an energy here. You had really a free energy already because the kappas are effective parameters, are temperature dependent, and so on. A nice answer to this, which I learned in the book by Phil Nelson, is that somebody's energy is another one's free energy. It depends on where you want to do the cut. I described the system at the Helfrich level, even though it's a free energy with respect to fluctuations in the tails and all of this. I ignore all of this. This is now effective parameters. I effectively now treat this as an energy, and then now keep looking at fluctuations on larger scale that I haven't yet integrated over, and those I'm now integrating over here and figure out the large-scale fluctuations. What is their thermal doing? Does that sort of answer the question? All right, and so these are flicker spectroscopy experiments that people can do as yet another way of how to measure rigidities and tensions in membranes. And I think I'll stop at this point here. There's questions. Yes?
Yeah, if we don't have the vertical boundary.
Yes?
Does this change this parameter?
Well, it changes the spectrum because now different modes are allowed. You would have to expand differently. You can't expand complex. You probably have to do in sines and cosines with boundary conditions. You will ultimately get the same answer. It's just more messy. Yes?
Like interface roughing and structure at all scales.
Yes, somebody asked, is the scale invariant? I can take this thing and go back in real space. I can ask, what is f squared 1/2 in real space? What's the mean squared surface roughness in real space? And the answer is it's a constant that I forget. But loosely speaking, it's about 0.02, about 2% of your size of your system. twice the size, twice the, so it's scale invariant in that sense, right? The height fluctuations just happily scale with the size of your system. They're not capped by some characteristic size, they just scale with the system size.
That almost looked like there was length scale, or is that just because the temperature is so low?
In the this is a scale, right? If you have a 10 micron, then this is, like, you know, on a you could see these things. And you're going to be, this is true for sigma equal to 0. When sigma is non-equal to 0, then there's a cutoff. It's no longer scale invariant. And when sigma is negative, then we have the problem. So if you push, then the denominator at some point blows up. So you have an instability. It's essentially a buckling instability. And that could amplify low Q modes even before you buckle. And so the power spectrum could look weird. So you got to be careful that sigma equal to 0 really is sigma equal to 0. Otherwise, you don't get the right answer. Angela. Yeah. There is, because the way I expanded the energy in terms of these geometric invariants, I was completely agnostic about where if I do a deformation, where the lipids were initially and where they're going to end up finally. There's no lateral strains that I tried to parameterize, something I would have to do if the surface were a solid. Then I get shear deformations that are not in here, shear deformations that are important. The absence of these shear deformations, which I can only define if I have a meaningful metric on the surface to begin with, not an arbitrary metric, makes the difference between fluidity and rigidity. It's a bit subtle how it comes out. For sufficiently weak fluctuations, that's okay. But for stronger deformations, in particular for any deformation that creates any sizable Gaussian curvature because of that theorem, you can no longer do that.
Why the sign on the square gradient square Gaussian thing where you transform why the plus here doesn't have the minus?
You mean why there's a plus here but a minus there? No. There's a plus in the energy. Where's the energy? Up there, there's a plus in the energy. But there's a minus in the Euler-Lagrange equation. No. You have two factors of I, one here, one here. That will give you one minus sign. Another minus sign happens from here that Q is equal to minus Q prime. And that will kill it again. And then you get a plus Q squared. That minus sign came from the I's. And Q has to be equal to minus Q prime. I replace Q prime by minus Q, and that kills that minus sign, and I'm back at plus. Right, it's a positive Hamiltonian. You better end up with a positive Hamiltonian in a different basis. Okay. Yeah, Leo.
Just a comment, the little slide we have that you pulled.
Probably.
Well, so, doing the single partition for when you Fourier transform a real function and you do the spectral decomposition, the Fourier transform has a relation to f star and f are related. Right. But so that means the modes are not exactly independent.
Okay, so yeah.
There's really harmonic oscillators.
Yes, let me make a comment on this. This is absolutely true, and this is infuriating whenever you do any of these things about mode counting. The moment you say, oh, exponential is so much nicer, but the mode counting becomes a nightmare to make sure you don't overcount. Exactly for the reason that Leo mentioned. And because this is so hard, and at some point it's going to be just sussed out, there is actually a note in my notes which says, if you want to do proper counting, this is what you do, and after some magic, it ends up that I was right here, but exactly because of a sleight of hands. That certain factors of 2 and factors of 1/2 that I just was very nonchalant about here just canceled, and everything's fine. But some miracle is under the rug here. Yeah. Yes, these expansion coefficients. This is not one expansion coefficient. This is 2 expansion coefficients, a real and an imaginary part. but they're not independent because of that. So the counting problem is just there, but it can be done. And this is the answer. All right, are we all hungry now? Off for lunch.